terms of our next event is in June, which is the summer social. There'll be more information on the website about that. So please do consider coming along to that. It's a good way of meeting people, finding out what else is going on with computing and IT in the Oxfordshire area. So finished all the introductions. I'll now hand over to Andy and ask him to take us through this very interesting presentation. Thanks, Andy.
Thank you. Hello. Okay. So hi, I'm Andrew Davis. I work for Andrew actually at the United Kingdom Atomic Energy Authority, and I'm going to talk to you today about digital engineering. Now, I have to admit I did use ChatGPT to help me come up with a clever title, which it did come up with, which was actually quite like, which is not your granddad's slide rule, digital engineering for the 21st century. So we'll talk a bit about what digital engineering is, how we'd like to apply it, and some of the early successes we've had in using it at scale. So, as with all of my presentations, I will give you a warning. There's a lot of material. It might seem that some of the concepts are disconnected, but I promise you we'll all hopefully coagulate together at the end. No presentation about the speaker should be missing who they are and where they're from. So I actually started life at UKA back in 2004 when I started at UKA Dounreay on the north coast of Scotland, the fast reactor program, and actually ended up working at Culham, which is where I wanted to work from being 14 years old and being fascinated with fusion. So I came a bit of a roundabout route. I finished my PhD in nuclear physics and then joined as staff. A couple of years later, I then went on a brief American trip for 5 years to the Computational Nuclear Energy Research Group, the Department of Engineering and Physics, University of Wisconsin-Madison. And then due to a number of political changes that were going on in the US in the 2016-2017 timeframe, I ended up making my way back to the UK. And since joining, I've had quite a varied bit of work. We've been working in a new area for UK at the time, which was engineering computation. I ended up being lucky enough to lead the STEP Digital Enablers Programme in Tranche 1. And I've been Head of Advanced Engineering Simulation at UKA from 2021 to now. I'm also fortunate to be a visiting professor of engineering at Swansea University, especially honoured because I'm not even an engineer. I consider myself an engineering physicist. Hopefully they see the value of what it is that we do. So I'll talk to you a bit about UKA, who we are, because some of you I'm sure don't know who UKA are. We were created by an Act of Parliament in 1954 when the government wanted to set up a new body which would centralise and look after the nation's nuclear research programme. And the role of UKA was to develop and provide Britain's atomic weapons, its deterrent, develop reactor technologies and do fundamental nuclear research for the power stations of the future. And through that programme, we built Calder Hall and the Windscale piles in the 1950s, the Dounreay fast reactor in 1956, and a series of reactors over the course of the years. And as time went on, different changes to law and parliamentary acts changed what it was that UKA did. So the first change really was separating out the fuel part of UKA to allow it to focus again on the research and weapons. And then shortly after that, it was decided weapons was going to be its own thing, which created what you might now know as AWE. And to cut a long story short, the last part of UKA that's left is the bit doing fusion. So the Culham site is this one down here. And all we do are nuclear fusion. Not that we don't have an interest in other things going on in the nuclear sector, but our role is specifically nuclear fusion. We historically operated on behalf of the European Commission the jet reactor, which ran very successfully from the late 1970s until very recently. And now we're left with running mast upgrade, which is a spherical tokamak, which is a more it's a higher efficiency device than a conventional aspect ratio tokamak. It also offers a number of unique technologies that allow it to operate in high performance, and the hope is that technology would lead to a high performance tokamak in the end of it. But our goals really are to lead the delivery of sustainable fusion energy, maximizing the scientific and economic benefit. With that, it's bringing growth to the UK economy to create a fusion industry that will allow us to export fusion technology around the world, to enable partners, so whether that's commercial partners or collaborators, to help us deliver and design and operate commercial fusion plant. And really what we do at UKE is a lot of the fundamental research on how we deal with going from the concept design through to the science and engineering of the devices. But first, I want you to imagine the year 2040, which is when the step reactor is meant to come online. And imagine the year 2040 as I imagined, or as Blade Runner promised, the year 2015. But imagine you're on your commute to work in your flying car, and you're imagining you're drinking, your Soylent Green or whatever it is, your food pill for the day for your breakfast. But your job, you are the project manager or the final delivery engineer of the world's first fusion power plant. Right? You are on the way to the office to install the last final bits in this wondrous machine that you spent a lifetime building. But there's a problem. The last component has not been designed to your specifications. Your life's work is at risk. What you need to be able to do is to really say, am I going to accept this component? And given how different it is to how it was designed, can I tolerate those changes? Or do I have to delay the operations of that reactor by however long it takes to make that new manufactured component? And that question is, what impact do small changes have on the operations and design of fusion power plant? That's largely the questions that we're trying to answer here. Is, given how coupled the system is, how can I be sure and confident that taking in this substandard design, what impact will it have on the rest of the system? That's really what a lot of the questions we're asking here are about. So I'll do this answer some of this through metaphor. So in honor of Paul Methven, who is the lead for the STEP reactor program, being an ex-admiral, I often do this through taking people through the design of ships. So as an example, in a 100-year period, the Royal Navy went from its very first steamship, which was the HMS Royal Georges, which you could look at it and go, well, that's just a sailing ship with a chimney they put on. And the space of 100 years, we get through to the last dreadnought-style battleship that ever existed. Now, bear in mind, our challenge today, where we are in the 2020s, gazing at the 2040s, thinking about what the power plants of the 2050s and 2070s look like, we're in a very similar position. We didn't know, well, it was not known when this first steamship was built, really the laws of fluid mechanics, which weren't really established until the 1840s. Thinking about how we do, sorry, I'm just going to minimize this little annoying screen. Thinking about how little we understand of material science and thermodynamics and how we manufacture steel. These dates I've put in indicate kind of the foundational year that the really deep understanding came from, how we either discovered the processes or designed how they worked or really commercialized a process. So you can imagine there's therefore an awful lot of uncertainty in how we could not really apply theory to design this steamship, nor did we do it here. And really, we did have a decent understanding of a lot of processes by then, but I'm not really sure a lot of theory was used in the design of this. We're in a similar process here in that we are at a fairly nascent stage in terms of looking at spherical tokamaks, yet we are needing to peer over the horizon at things that we don't yet truly understand and how that will influence design. And that's really the challenge we have. And this challenge stems from a number of areas. One of those is there simply isn't enough time. There's not enough experiments. that we can do in between now and 2040 that will de-risk the design in a major way. That's because to really de-risk the design, you need to have a deep understanding of operations in a high heat flux environment. So the heat fluxes we expect to see in the first wall of these fusion devices is between 5 and 20 watts per meter squared. To give you an example, integrated over the whole device, that's a heat flux equivalent to at least 1.5 fission reactors. The output of an entire fission reactor, just heat flux on that first wall. At the same time, it must endure tremendous neutron fluxes. So 10 to the 15 neutrons per square centimeter per second. That's about 10 times higher than the neutron flux we see in fission reactors. These energetic neutrons cause transmutation and radiation damage, depositing further heat volumetrically. The temperatures near the first wall are in excess of 2000 Kelvin. The plasma itself will erode first wall material and redeposit material around the device, all at the same time, whilst experiencing magnetic fields in excess of several Teslas. And it's an unfortunate truth that the combined load, all of these things being available to us experimentally all at once, are only found inside an operational fusion reactor. So if you want to test these things, you kind of have to build one. Further, economically, we need these materials to last between 3 and 5 years. And in that 3 and 5 year period, they will experience radiation damage of 200 dPa. dPa is a measure we use of radiation damage. And steels that were used in the fission program have not seen 200 dPa. They've maybe seen at most maybe 18 or 20. So the irradiated steel is more like Swiss cheese than it is structural steel at the end of that 200 dPa cycle. So we have to have those steels working because the quantity of material we're talking about is billions of pounds of material in the first wall. So we can't be replacing that on a regular basis, otherwise fusion is simply uneconomic. So if you look at how anything largely has been designed over the years, we start out with a Cambrian explosion of concepts. So here in the early days of flight, you can see there are all sorts of ways that people try to kill themselves by building biplanes, monoplanes, triplanes, tri-wing, 3 engines, 5 engines, 4 engines, engines at the back, engines at the front, engines above, and all things were tried. And then over time, we kind of centralized in this, what we call the engineering S-curve, where the technology is quite mature. And as you approach the technological limit, actually, there's very little iteration between the designs. Like the difference between the very first part of these aircraft and the last part of the aircraft, of course, in terms of radar cross-section is fundamental, but in terms of the way they're designed and operated, it's a very similar process. Applying that logic to fusion, we have a bit of a problem because we are down the very early part of the development cycle, where we are in a this S-curve gradient is really quite low. And we need to get it up to the point where we're looking at step, which is actually quite high up the S-curve. Now, the way you'd normally do this, if I was to give you a design challenge, I always use the example of a toaster. Let's say you were a toaster engineer and you were tasked with the task of designing a new toaster. You would first of all figure out what it is that your problem is, and your challenge is, well, design a new toaster. You'd go, okay, well, I'll pop down to Argos, I'll buy 15 different toasters, and I'll analyze the behavior of all those toasters. What can I do differently? Maybe I want a more uniform crisp on my toast. Maybe I want a particular pattern. You'll then figure out from those systems the gap in the market. You'll develop your solution, you'll gather feedback, and you'll iterate. And this is how nearly all products that we have today are developed, and they all happen at the top of this engineering S cycle where iterative design happens. But we have to go from this part of the curve to this part of the curve without going down the middle. And the reason for that is simply cost. Fusion plants, like fission plants, are simply capital expensive. If you look at the construction cost of ITER, that's not including the operation cost, just the construction cost, ITER would cost around about £22 billion. Hinkley Point C, which should have been a concrete in the ground type job, I think the most recent cost estimate has been £40 billion. And SMRs, obviously much smaller fission reactors, I think of the order around about 3 billion. The vast majority of some of this cost, in the case of fusion, is concrete, because we've got lots and lots of concrete. Magnets are expensive, and the volume of material steel we're talking about are expensive. And many of these materials have no existing supply chain. This graph, though, should give you some solace. This graph shows, by Sam Wurzel from MIT, shows Ni tau E, or N tau. This is the number density and the energy confinement time. So one of the ways to get a lot of fusion is to keep your energy well confined in the tokamak and make it dense. The more dense the plasma, the longer you keep the energy confined, the more chance there is of fusion. And on this bottom axis here, we have the ion temperature. This is how hot, the measure of how hot the reactor is. So Zeta was the first device that was built by A.E.R.E. Harwell in the 50s. And then over time, you can see these other devices pop in. One device of note here, T3, as this GIF replays. This was the first tokamak, and this led the world along this explosion of different tokamaks. But the nice thing about this straight line is this is effectively Moore's law for tokamaks. So if you're on this line, then you are effectively doubling your confinement every step. And the bit we're really interested in is up here, where you'll see jet was around about here, was almost at 1, this green line, which is the Q value, the engineering Q, the measure of how much energy you get out to how much you put in. So for a power plant, that has to be greater than 1. ITER's targeting 10. There's a problem, though, which is if you want to do design by iteration, which is how we traditionally design things, the cost of failure is huge, because the way that energy confinement, because of how confinement scales, which is the square of the magnetic field, the Q of the radius, eventually these designs simply become too expensive for us to fail. So the cost of failure is of the order of billions of pounds. So we can't fail, right? We cannot build one of these devices and not have them work. That simply isn't going to be acceptable. So in summary thus far, we traditionally use design by failure. We can't do that for that trend to continue. There will not be enough of the right experiments to de-risk tokamaks before 2050. And many of the models we actually use in tokamaks have some uncertainty around them. Thinking of it from a regulatory standpoint, often we demonstrate safety through margins, and margins are determined by experiment, or through long and arduous demonstrations of robustness. We don't have that. There isn't the data, right? There is no data to base a fusion design code on. So the only thing left to us is to demonstrate this through in silico, to do all of this through physics. And to do that, we'll have to have major advances in the way we do simulation, to the point where we can simulate the complete tokamak, not just the plasma. So many countries have what's called a whole device modeling program, and ironically, the whole device modeling program often stops at the plasma. So in terms of whole device, I always found that term quite ironic. We're also blessed that we live in the radical uncertainty regime. So we live in a regime where we simply don't have data to fill the gaps. So how we address some of those problems is going to be one of our real challenges. So what we propose is to use detailed multiphysics modeling and simulation to give us insights that we can get that wouldn't be possible through traditional approaches. So by basically wrapping what you would normally do with advanced science and modeling and simulation and first principles theory, we can fill some of the gaps. However, there will be some uncertainty and there will be some unknown unknowns. And one of the ways to address that is by adding in more physics, and I'll talk about that more in a moment. So I'm sure you all are aware of the phrase, a jack of all trades is a master of none. What we never talk about is the next bit, which is a jack of all trades is a master of none, but often is still better than a master of one. So one of the things that makes fusion difficult is that it is a mixture of domains, and it's the interfaces between domains where complexity happens. So having more people know about more domains is one of the ways to bring down some of these barriers, and that's what digital engineering is about. When I originally produced these slides, I often talk about what other people consider digital engineering to be. And that often comes from their experience and where they are, often the company. Quite a nice one is from BAE Systems, which is that digital engineering's purpose is to accelerate the development of complex products, systems and subsystems by overcoming the established engineering disciplines, while still addressing each engineering problem. Traditionally, when you take the standard approaches, how people develop complex products, you get bogged down in complexity. Simply partly through interfaces, which is how we exchange information between people, or how we've just segmented the problem. And what digital engineering allows you to do is massively accelerate that. One of the ways to do that is through the use of integrated digital tools, methods, and models across the entire life cycle of complex systems, i.e. from concept, design, how the materials are made, how those materials turn into components, how those components turn into the whole system, how that machine is operated, run, and then decommissioned. And it emphasizes the use of digital models rather than traditional approaches, which is a document-based process, which is, you do some work, you write a report, you do some work, you write a report. That simply can't scale into the area we need to head into. So one of the approaches is to basically do model-based systems engineering, which is you take digital models, which you use to define requirements. For example, my component must not experience a stress more than 7 megapascals. That becomes a requirement, and then you can tie that to the output of a simulation, which shows that whether that is the case or not. We need to have the authoritative source of truth, often called a digital thread or a portal to truth, but this is a place where everyone can get a single view of what's really going on in the design. Integration of the entire system across its life cycle. So, for example, being able to trace exactly which bolts were used, where those bolts came from, the impurity levels of contaminants in those bolts, how that would impact radioactive waste, and how that all ties together into a seamless digital thread is really important. Interoperability between tools. One of the things that really bogs down standard approaches is incompatible commercial tools which can't really communicate between themselves. Really, a huge accelerator is automation, being able to use simulation, optimization, and machine learning, high-performance computing to give us faster and smarter decisions. A huge power-up, though, is collaboration across disciplines. So I think of this more between different physics disciplines, but actually think about how we can collaborate with operations and procurement in a shared environment so we can all understand in our own domains what's going on in the design is really critical. I will show you some examples now of this. In terms of the lifecycle and collaboration, I will give you a brief example of what we've done with NVIDIA Omniverse. In terms of interoperability, what I can give you, and then a little bit on automation, and there's much more detail coming up. So NVIDIA Omniverse is a product produced by NVIDIA that they actually use to design their graphics cards. So NVIDIA nearly went bankrupt a number of years ago, and one of the things that really saved them, and actually what made them so competitive, was that they really invested a lot in the simulation to understand how their graphics cards worked at the electronics level, heat performance, cooling, and that actually became NVIDIA Omniverse, which is their platform for doing heatsink design on GPUs. And we can leverage exactly the same technology to do collaborative design in the cloud. So here's an example of somebody in Manchester who's operating on one of the mass models. And we also, so I'll wait till it goes back through again, but an engineer at Cullum who's doing their own work. So it's a distributed view of the same system and kept in sync. When somebody makes a change up in Manchester, that change is reflected back down in Cullum. So we'll all have a consistent view of what's going on in the system. Another example in interoperability is when doing coupled analysis. So traditionally, engineering domains would produce a single model for each of their physics. And that would be different for each one. So a mechanical engineering model will be different from a thermal model, different from a fluid model, different from a magnetics model, and so on and so forth. One of the approaches we're trying to put forward is actually you don't need that. You can have one model. If you can have one model which can be sent to different physics, then you can really have a properly integrated way of doing the analysis. This is an example of work we've done on our masked upgrade system. This is showing you the mechanical loading due to stress. At the same time here, I'm showing you on exactly the same model, literally the same model, you're seeing the neutron field produced by the device. This allows us to do things like pretend what would happen under in a really heavy neutron radiation, how that impacts the mechanical behavior over time. But this is a microcosm of what's possible if you add in thermal behavior, add in what happens to cooling systems. We have a chance to really understand and allow emergent phenomena to arise from the coupling of this physics, which is heretofore not really being done. Examples of automation. This is a model that we produced of Chimera, which is a high heat flux testing facility busy being built in our second site up in Rotherham. It has a suite of diagnostics, but the real thing I want to show you here was this was novel a number of years ago. But what this is the whole system being solved for its thermal mechanical performance at the same time. And when doing it in detail, you get to produce a lot more emergent behavior, even with just two physics, than you otherwise would normally see. And as this video plays again, you'll see, if you watch the front of this system, as the system ramps in time, it's getting hotter and hotter and hotter, you'll see a really small blue pressure wave drop through, where it kind of pushes through the system. It just so happens that this is the longest conduction path from the input or the outlet. So the system's kind of catching up with the heat wave that's propagating through it, which you otherwise wouldn't see on simpler models. But that's really simple. It's not a particularly important effect, but the point is you can predict it and see it, which you can't do with simpler models. Okay, so we've talked about some examples of what digital engineering is, but why? What does it get us? So the real benefits we see are faster development cycles. So you can, if you had a system which had more of the physics in, you could do your design quicker by having scalable multi-physics platforms, by failing early when we realize something's not going to work. It'll have lower life cycle costs because you've done more to integrate the design and changes earlier. With everyone having the most up-to-date information, you aren't making decisions on stale data, which otherwise happens. You obviously have improved system quality and reliability because we have all the information available to everyone all the time. Much better traceability and auditability because you can have a full series of changes and records of what's happened, what decisions have been taken, and why. And of course, better adaptability to change. One of the key things that happens in fusion is somebody builds a new experiment and we suddenly realize, oh, this model was wrong. We need a new model to describe X, Y, and Z. And we have to bring that data into our model and see how that brings the changes. So again, having these platforms and automated systems really allows us to be much more adaptable to change. And in our case, particularly in fusion, it's about reducing risk, shortening lifetimes. And I think in reality, it's possibly the only way we can actually deliver fusion is by having a huge push on simulation to fill the gaps the experiment cannot fill. So digital engineering, I view different parts of digital engineering in different ways, but you can take some of the fundamental disciplines of what digital engineering is, like computer science, the human-machine interface, electronic systems, and this Venn diagram of how different bits overlap are all different facets of digital engineering. So looking at how the human interface with electronic systems is an example of AR and VR, and how we can use that in our visualization just to understand what's going on in our systems better. When you bring together computer science and the science and the physical sciences, we can really get much better simulations. So this is how this is my conceptual view of what digital engineering really is. What is a digital engineer? So it's a relatively new field, really. But because of that, it happens and changes happen a lot. And if you don't keep up with changes, you'll get left behind, and technology changes fast. So you've got to make sure you are riding the crest of the wave, what's going on. But ideally not so high up the wave that you're also be the first to fail. You can be a little bit behind. You can take advantage and ride that wave in progress. You've really got to be digital native. And software and APIs is the natural language of digital engineering. So people who can program really need to be, they are also digital engineers. Soft skills are really important because you are the bringer of change, and you need to help people adapt to those changes, and therefore effectively communicating why the changes need to happen, how they're going to happen, and help people to make the changes is something that's desperately needed because people are not usually a fan of change. I can't say there is any particular one skill type, but I think diversity is really important because it takes a village of skills to deliver what it is we need to deliver. So different physics domains, different backgrounds, different programming languages, they're all really, really important. And persistency, right, is be willing to have a go. You probably won't get it right the first time, but you will get it right eventually. So persistence is really, really important. So I'll talk now a bit on simulation. This is really kind of the bread and butter of the talk, is why simulation is so important to us. So really you can summarize our simulation challenge as we need to simulate everything, everywhere, all at once. So many of the fields that arise in a tokamak, so the plasma, which sits in the middle of the device, produces radiation. It produces neutrons. Those neutrons bounce around. They actually often bounce around and come back on themselves, go across the other side of the device, bounce around over here, come around over there, bounce down there, before eventually being absorbed. So that neutron field is actually coupled across the system. Therefore, if I make changes to this component here, it naturally has an impact on all the system around it. So there's no neat way to segment the separation of concerns in a fusion reactor because you're dealing with a globally coupled system. Similarly, the electromagnetic field, which we produce by large sets of magnets, these are these sort of coppery sort of color magnets in this cross section of ITER, produce tremendous forces. I mean, they produce magnetic fields in excess of I think 9 Tesla. The structural steel reinforcement required to contain all those coils is not insignificant. The structural forces and gravity alone, the mass of a fusion reactor of ITER is something like 43,000 tons. So that's greater than an aircraft carrier, all sitting on gravity isolation pads in case of earthquake. So there's a tremendous amount of force involved just from gravity. We've talked about high temperature. We need to talk about chemical transport, so tritium transport. When tritium is not burned in the plasma, it can kind of get stuck in the first wall surfaces. It's also produced in nuclear reactions throughout the device. So modeling and understanding where that goes, which is coupled in time, like with temperature and the neutron field, all of this together brings for quite the simulation challenge. We also have the need to compare against experiment. So we often want to compare what we've done. This is in the true engineering sense. We have made some physical asset and we'd like to understand what's going on. One approach is something called image-based finite element modeling. So we can take relatively small components. So this is what's called a divertor monoblock. These sit on these are each thermally isolated from one another. They sit on a copper chrome zirconium pipe, and they bend around this entire component. So these stripes you're seeing are all these stripes on that component there. When these things are made, they're made through welding and brazing and various heat treatments, and the exact way that this material is bonded together impacts its thermal and mechanical performance. So we can take many X-rays of these systems, figure out exactly where the adhesion hasn't happened, there's been separation and cleavage, and then we can see and understand in simulation terms how that will impact the performance of that component. Critically, we can take technologies like digital image correlation. So this, I guess, is a paintball gun. Got a paintball gun, yet firing a marble. This is covered in speckle paint, so it's kind of like you spray paint it first of all white and then cover it in these black speckles. And what you can do if you take lots and lots of photographs, you can between each image see how those speckles are moving around, and this gives us a live view of the mechanical strain or the displacement of how this component, this case, this paintball gun, is actually mechanically changing. So you're seeing that the pressure wave, the force of the gas of the ejection and what it's doing to the mechanical structure as this wave bounces back and forth. If you combine this image-based finite element view of the world along with digital image correlation, we have a way of properly validating our mechanical simulations to really show if we understand what's actually going on inside our components. This necessarily, though, brings a bit of a challenge because it means we need to have software which can handle the increased detail that's required. That means we have to have software that can scale. Previous work has already established the need that, generally speaking, the commercially available tools don't scale very well. That when you take, this is an unnamed solver, and throw it at a problem that you'd like to get, either when your problems become bigger or you'd like your answer faster, you can throw more CPUs at it and you can see in this particular problem, the code, you no longer get any speed up. As an example, if we then amplify the level of detail, so let's say, for example, I wanted to take this, this coil. This is an example of a mechanical analysis of one of the coils in our masked upgrade device. This reflects the simplified model that was used in comparison to the global problem of the masked upgrade, which I'll show you later. But these times here show that this is not a scalable solution. If my problem gets 300 times bigger, I can't be waiting for 224 days for a result. That's clearly not. That's not a goer. So how can we do that, right? I've interspersed what I consider humorous quotes throughout this. So whether you find this funny or not, I hope you do. But the good news about computers is that they do what you tell them. But the bad news about computers is also that they do what you tell them. So you are the bearer of the problems. What was clear throughout the early part of my career, so I was working in software development for Fusion from the year about 2000 onwards. So I was in the middle of the golden age of programming, where you could do literally nothing and your code would get faster for free. There's a famous quote from a neutron scientist from Lawrence Livermore National Lab who crowed about how good his software was. And it turns out actually it was just the scaling of the hardware. You were getting much better single thread performance. But this was my early career, and once my professional career established, actually it was clear single thread performance was dead. We really had to worry about how we deal with this increasing number of logical cores to get the performance we needed to. So the exascale has arrived. We know that we have CPU and GPU systems. There are different ways of programming them. There are different models. We typically prefer performance portability because we don't want to standardize on a particular hardware vendor. But that brings further challenges because some of these systems don't allow true performance portability. In that mix, we have new languages, which is difficult when you've got large research programs to pivot them. But that all comes with us to where we get to the exascale, where the exascale firmly arrived with Frontier, Aurora, El Capitan. The US met its exascale goal, which is great. This shows you the HPL, which is the High Performance Limb Pack benchmark, which is not a particularly useful benchmark, but that's what is used to tell whether these codes have met the exascale. If you look at what you as a typical user would have access to, and this is my home desktop, this is kind of the level of compute that you get on your desktop right now. So right now, you at home, well, me, have the same compute capacity as the world's biggest supercomputer in 1996, which is amazing, actually. You've got a tremendously powerful machine. And actually, if you had an iPhone, the iPhone's probably not far up here when you consider the iPhone's GPU. But how we use these systems, these large HPC systems, to deliver useful science is still challenging. Taking your software, which runs on your desktop, and trying to get it to run on thousands of cores is tricky. Therefore, we need some solutions at scale, right? We can't be bound by cost. So if my problem size doubles, I can't need to pay double the license cost. So if my simulation size increases by a factor of 10, we can't be paying 10 times as much money. If we are bound behind a price barrier, we aren't going to be able to make progress. No time to solution. If my problem size doubles, I cannot double my compute time. If my problem size gets bigger, I can't have a barrier in the way. And therefore, if I also want to be able to do lots of things at once, which is scale horizontally, I need to be able to. And if we have that adaptable, scalable approach where we can scale both horizontally and vertically, then we can do a lot of interesting things. So a summary of where we are so far on this. So traditional approaches limit throughput, often because they're manual, built on approximations, and humans do it. Manual mesh generation is tedious and it's slow, it's not parallel. Commercial solvers don't scale well. And if we can get the engineer off the desktop onto solutions that do scale, then we can really do some good. An example of that is how we can use HPC to accelerate. So we can get faster simulations by having software that can scale. With the application of AI, for example, in similar approaches. We can do design space exploration. If we can scale both vertically and horizontally, then we can do parallel parametric sweeps, we could do sensitivity studies, we can do proper uncertainty quantification. We can really get into an area where we can do design optimization properly through topology optimization, genetic algorithms, through different approaches. And by doing that through HPC, we can actually do a lot of the prototypical development and validation computationally, without doing as much physical testing as we used to. As an example, the system I showed you earlier on, which was from Chimera, that occupied at the time, I think it was about maybe 28 million elements or something. It kind of was a big problem at the time. It consumed a decent chunk of our resources for about half an hour. But as you scale up, an image I'll show you later on of a whole device mechanical model took around about 128 million elements. And how when we get to the whole reactor scale, I don't know what the limit is. We really don't. But we have to move in that direction to get more physics in. So that's these large-scale multi-physics calculations, essentially your hero runs, doing lots of calculations on a large HPC cluster, all at once to study a lot of physics. You can also do optimization and in UQ. So some examples of large-scale multi-physics. This is an example of work done by one of our engineers, Luca Reali, which took the detailed mass upgrade engineering model we have and really scaling out to push the limits of what we could do. We got this runtime down in the end into about 6 minutes by throwing different algorithms at it. But it really shows that what people would have thought impossible even 5 years ago is eminently achievable now and agrees well with reality. Taking detailed fluid simulations, we can really push the limits of approximation. So traditionally, we would take this kind of 1D version of a cooling system. We can now do full system turbulence models on a regular basis, but actually being able to compare those turbulence models against the full DNS, which is the gold standard in terms of fluid simulation, being able to actually prove that our approximations are giving the right answer and give our engineers confidence in their design process. An example of that is how we do blanket design, breeding blankets. They are truly where the rubber meets the road of infusion. They are exposed to the high radiation flux. They're exposed to magnetic fields. They're exposed to high temperatures. They have to run for years on end. They have to produce tritium. It's a really tricky environment in which to exist. You need to take a neutron source, which comes from a bunch of physics simulations. You then have to do a global simulation of where the neutrons go, because that influences what goes on the blankets. Just as a side note, the ITER reactor, when it turns on, will produce 10 to the 20 neutrons per second, which actually over 24 and a half weeks is a kilogram of neutrons. I'm not sure if you've got any physical feeling for what a kilogram of neutrons are. That's a lot of neutrons. That's an awful lot of neutrons. So then we want to get into the regime of how we can really go about designing these blankets in detail. We do that through coupling different physics simulations together. So neutron transport, electromagnetism, fluid simulations, tritium transport, bringing that all together into a single ecosystem that allows us to do simulations of all this physics at the same time, coupled together, which allows us to get this dynamic feedback. An example of a really nice detailed MHD simulation we've recently done, which is possibly the largest engineering MHD simulation ever done, gives us an understanding of what goes on here in a blanket where when the magnetic field is off, now the magnetic field really suppresses the turbulence in the blanket, which will have benefits to our engineers who can neglect things which we now know aren't important. Similarly, we can use HPC to optimize. Here's an example of an optimization of a tritium breeding assembly. We can say, well, I want to vary this parameter 1 and this parameter 2. I don't know how thick this should be. We'll just we'll take a Bayesian approach and let the system decide for itself. We want to tessellate as many of these things together as we can. And if we do that, we have this system where we have a broad dispatch of information onto a HPC system. We evaluate a given instance. We produce a given instance of that problem. We run it through a multiphysics analysis. You get your figure of merit out at the end, and then you figure out what you're going to do next. And you go round and round this loop until you figure out, until you've approached your optimum. An example of that is that exact model I showed you earlier on. This red cross was the human best guess, and this black cross is what the machine came up with. So it basically does an initial scan of points and then starts clustering more and more points in the area that are interesting. And through that, you can actually get a much better performance, which is really great, because often when we apply these optimization techniques, you don't always see a better product. But in this case, we really did. All of this comes together to give us digital twins, which is a joy that is shared with a twin, is a joy made double. So a digital twin is something you may have heard used and used and used. We have a very specific definition of what we mean by digital twin, which is that of Greaves and Vickers, who really are the original author, the original people behind the idea of digital twin, which is effectively that the information to do with the digital version of a real asset can be a thing on its own. It can be you can do things with it that you can't do with the physical system. In our case specifically, we must use it to predict future state. We have to be able to look into the future and figure out what will go on. It's inherently multi-scale. It must allow for emergent behavior, because we already know it's the unpredicted things that happen that will be a problem for us. So we have to be able to allow those things to emerge computationally. Fortunately, Greaves has this test of virtuality, which is kind of like a Turing test for digital twins. So you can kind of test, do you have what they would consider a digital twin by, do you meet these requirements? How we do that, we are marching towards this idea of a digital twin. So how we take the detailed plasma simulations, which is the big grunt on the exascale systems, so how we do large-scale gyrokinetics and MHD simulations in blankets, how we can then use things like Gaussian processors and active learning to build emulators, to build reduced order models, which we can use in a fraction of the compute time, but to get the same results. How we then can link those with detailed simulation of plant, of how we couple radiation damage to these other models that we talked about. And we're also building other aspects, how these things fit together. We started out with kind of single domains. We're slowly bringing in other domains together. And the end goal is to bring them all into this one system that allows us to see what are all of these emergent properties that come from the system. This is not a journey that's unique to us, actually. using modern HPC systems to do complex engineering design is done on a regular basis. NASA do it to help them design their rockets. Argonne use it to design fission reactors. What we're saying here isn't heretical. What's different is the scale. We have a much stronger coupled system than most places do. We have a much higher level of fidelity than most other applications do. But we can transfer and take a lot of learning. Whatever we can apply in our system to fission reactors will be a way we can prove that if we can be predictive in fission reactors, then we have a decent chance of being predictive in fusion reactors. That means we want to make best use of our experiments because we have so few of them. We need to be able to see how we can use the right set of experiments combined in the right way to allow us to investigate this coupled behavior. And critically, we have to look at this actively cooled combined effects. So applying our tools to other nuclear systems is really, really important. One of my favorite quotes is, this is the last slide now, by the way. Any idiot can build a bridge that stands, but it takes an engineer to build a bridge that barely stands. So I hope this is not a denigrating comment to engineers. This is a very respectful comment that engineers take complex phenomena, build rules, and have the ability to then build things from that. The challenge we have in applying traditional engineering techniques is that in our world, in the world of the engineers of old, if you had a bit of iron, you knew how iron behaved because you built things out of iron before. It was heretical to build a bridge out of iron, which is why you can go to Iron Bridge in Shropshire, and that's such an amazing thing. And now we build things of iron all the time. The difference there is, though, our materials change. When you put them in a fusion reactor, they will become degraded, and the things that you thought you knew about it are no longer true. And actually, the digital challenges facing fusion aren't unique. They're present in many areas: hybrid electric flight, self-driving cars, advanced fission. And one of our collaborators, a chap called Martin Aston, has been working diligently with government to create something called the Brunel Challenge, which is the need for us to re-engineer engineering, to take a more pragmatic approach to how we do this. And we do hope that this one day will get funded. So last slide. Digital engineering and simulation must deliver fusion. It will be a driving force in how we deliver fusion. The more benefit we can pass to industry, the traditional engineering industries, to upskill and embrace HPC, particularly the engineering sector, because Britain has an excellent engineering sector. And if we can get those upskilled, then there's some tremendous things that could probably be done. The journey isn't unique, so we do have friends in different places. But doing everything that we want to do, we really hope that this will enable us to use computation as the third mode of discovery alongside theory and experiment. So really my final quote is, to err is human, but to really foul things up, you need a computer. And that's me done. So thank you very much. I'm sorry, a little bit over there.
Not at all. That was brilliant. Thank you very much. Very, very interesting. I was encouraging people to pose questions through the Q&A during the talk, and we've got one in there already. And the first question, you can probably see it yourself, but I'll read it out so everybody can see it. Is the UKA STEP project collaborating with ITER, contributing and or taking research results from them, people being part or of both?
That's a really good question. Not directly contributing to my knowledge. I believe we are in a tricky situation in the UK in terms of how we access ITER. I hope that will be addressed in the coming years. But my understanding right now is that we aren't allowed to participate in ITER, having left the EU. That's my understanding. Maybe you know, maybe you can recall the reasons more than I can. But I'm pretty sure that we are.
Yeah, so we're in a kind of stasis at the moment. There are various negotiations that go on at the government levels. We can work with ITER via third parties, and we're looking forward to the sunny future where we can go back to working more seamlessly.
Yeah.
I don't want to get too much into the politics here. So thanks again, Andy. If anybody wants to pose any questions, given this is Zoom webinar, you'll need to put your questions in the Q&A. nobody seems to be putting anything at the moment. So I think do let me pose a question for you, Andy. In terms of digital twins, look, there are lots of digital twins of complex systems that are easier to model, like the gas supply, the railway network, and stuff like that. Do you think our digital twin challenges can learn from their approaches, or are we going to have to develop new approaches and new ways of doing things?
That's a really good question. So, the digital twins that I've seen typically are of much simpler single domain physics. So they don't have to worry about the cross coupling. So they can do a lot simpler things. They can scale in a different way because their problem domain is a bit simpler. They can rely upon much simpler models than we can. Um, so I think that almost certainly yes. I think there will be definitely things we can learn from the digital twins currently deployed. Things like a company we do a bit with Digilab have done digital twins of water networks, for example. I'm sure there are things we can learn from those things, but we do also have our own unique challenges because we don't have digital twins often rely upon vast sums of data that we simply don't have. So that we do have challenges around data-centric approaches because of that, which I hope's not too much of a get out, but so yes, but I think because we do have differences, we'll also have our own challenges.
Thanks, Andy. Okay, so last chance for anybody in the audience who wants to pose a question to Andy. You've obviously given such a complete and excellent talk, Andy, that you've answered all the questions. So
Oh, absolute stunned silence.
I'm just checking the chat to make sure nobody's put anything in there as well. So nobody else is posing any other questions. So in which case, it's still a lovely evening out there. So I'm sure people will want to get away and enjoy the sunshine or the warm evening. Andy, thank you very, very much for an excellent, informative, and interesting presentation. Uh, we have recorded this, and with your permission, we'd like to put it up on the website so that people can watch it. I'll talk to you about that afterwards, just to confirm you're happy with that.
Okay, no
But
problem.
otherwise, thank you very much. Enjoy the rest of your evening, and thank you to everybody else for joining us. As I said at the beginning of the talk, the next event will be in June, and it will be a social event in Rewley House in central Oxford to bring together people and talk about what presentations have gone through the year and things like that. Hopefully, Andy, you can see those clapping hands. I
I can.
wonder you wouldn't be able to hear the clapping, so everybody's obviously really enjoyed it. So thanks, everybody.